Make sure it's unmuted. It looks like it is right now.
Make sure it's unmuted. All right, hi everybody. There was a little technical difficulty there. So in this video, we're going to take a look at lesson 8.4 part 2, which is going to be area of circles. So we're actually going to use the area of a regular polygon to help us figure out the area of a circle formula. So before we do that, let's go ahead and do a warm-up. Let's find the approximate perimeter of the shape. So we have a regular pentagon. We know that we have two formulas to use for area. One of them is 1/2 ASN, and one of them is 1/2 AP. And that's the one that we're going to pick because we are looking for the perimeter. So in this case, we know the apothem is 6 centimeters and we know the approximate area. So we're going to go ahead and substitute the area in. 1/2, the apothem is 6, and the perimeter. I'm going to go ahead and simplify. 1/2 of 6 is 3. And then I'm going to divide by 3. And my perimeter is roughly 43.6 centimeters. Alternatively, you could solve for S, which is the side length, and just multiply by 5. So again, what is the formula for the area of a regular n-gon? Well, we already talked about this, and we're going to call it 1/2 AP. And the basis for this formula, remember, was isosceles triangles. Remember how we created these isosceles triangles where the apothem was the height, and then we multiplied by the number of triangles we had. And so let's think about this. The apothem was also a reference to a circumscribed circle. So if we think a circle around our pentagon, the apothem is like, quote, the center of the circle that's circumscribed about the, the pentagon or whatever regular polygon we're talking about. But here, it's not actually a radius yet, but I want you to think about this. Because as the number of sides increases, the apothem gets closer and closer to the radius of the circle. It's circumscribed. And as the number of sides increase, so let's say again, instead of us having a pentagon, let's say we had, something with 12 sides or 14 sides, or closer and closer. As you can see, the perimeter of our yellow or orange inscribed shape is closer to the circumference of the circle than the pentagon is. So as the number of sides increase, what happens to P? It approaches the circumference. Again, of this circumscribed circle. So this is what's going to happen. We start with our 1/2 AP formula. Okay. What we're going to do is the n-gon, the n is going to increase. The number of sides is going to increase. So then what's going to happen is the apothem gets closer to the radius and the perimeter gets closer to the circumference. Now right now this doesn't look like very much. Circumference, which our book will not teach us until chapter, our book actually taught you, sorry, in chapter 9, but I teach it a little bit backwards. The circumference of a circle is 2 pi r. And so what's going to happen is we're going to have 1/2 times the radius times 2 pi r. And this area, remember, is now no longer going to be the area of a polygon, but it's going to be the area of a circle. And as we simplify, 1/2 times r times 2 times pi times r, the 1/2 and the 2 simplify out, the r's combine, And this is our very famous pi r squared circle formula. It's worthy of noting that the area of a circle can only be found using the radius, not using the diameter. So if you get a diameter, then you must use a dividing by 2 to find the radius. So let's do a couple things. If our radius is 3 inches, what would our area be? And we're going to leave our answers exact, meaning we are going to leave pi in the answer. So let me show you how that works. So the area of a circle is pi r squared, and notice I have equal signs here because I'm using pi as a symbol, and so I'm not using its decimal approximation. I substitute 3 in for my radius. So 3 squared is 9, but when I rewrite this, I'm going to put the 9 in front of the pi, kind of like it's, the pi is almost like a variable, even though it's actually a value, a number. And then, so the area of our circle is 9 pi, and of course I want to put my area square area, inches squared. Let's look at the second one. If the area of a circle is 3 pi square inches, what is its diameter? So let's take a peek. Area is 3 pi square inches, excuse me. Area is pi r squared. Substitute 3 pi in for the area. Now what's going to happen is we're going to solve for r, right? So the first thing I'm going to do is divide by pi on both sides. I want to work into my variable. And that's going to give me 3 is r. And then I'm going to take the square root. Now, because square root of 3 is irrational, I'm just going to leave it as square root of 3. And then because the radius is half the diameter, to get the diameter, I'm just going to multiply by 2. And so the diameter of this particular circle would be 2 square root of 3 inches. Again, that might feel awkward because we have a square root. If you really wanted, you could put this in your calculator, and if you do 2 times the square root of 3, you're going to get a decimal about 3.46, so about 3.5. But I like to leave things exact. In this case, you should be able to, so let's looking at example 3, we want to be able to go from the circumference of a circle to its area. So again, the circumference of a circle, we can use 2 formulas, 2 pi r or pi d. But because area only uses radius, I'm going to use 2 pi r. I'm going to go ahead and substitute 12 pi in for circumference, and I'm actually going to divide by 2 and pi as one sort of chunk. Pi divided by pi cancels out, and 2 divided by 12 divided by 2 is 6. So my radius is 6, and then in my area formula, I would substitute 6, and so the area of this circle is 36 pi square inches. Let's do a couple that are a little bit more interesting. Not that those weren't, but those were some pretty basic ones. So let's take a look at the area of this shaded region. So we have a circle plotted in the plane, and we have an inscribed rectangle. And they give us a couple key points. So because this is a rectangle, we know that there are some symmetry happening. Okay? So this point is 3, 4, so that we can assume that this is negative 3, 4. We can assume this is 3, negative 4, and we can assume this is negative 3, negative 4. And that helps us because now we know the side lengths of our rectangle. This goes from negative 3 to positive 3, so that has a length of 6. And this goes from positive 4 to negative 4, so this has a length of 8. I also noticed that we have a circle circumscribed, and we have this point here on the circle, which is 5, 0. Now the radius here is centered at the origin, and so if this point is 5, 0, that means the radius of our circle is 5. First thing I'm going to do is just going to get myself set up with what I want to do. Because I want to find the area of the shaded region, what my idea is, I'm going to take the circle minus the rectangle. So I'm going to take the area of the circle, which would have given me this whole thing. But then when I subtract the area of the rectangle inside, it leaves me with just the shaded pieces. And I'm going to write down my formula. Pi r squared, and my rectangle is BH. Then I'm going to substitute in my values. That's a 5. And my length is 6, and my width or height is 8. And then I'm going to write this as 25 pi minus 48. And I'm going to leave this exact. I could punch in 25 pi minus 48 in my calculator. The other thing that I don't want you to think that this is a smaller number. Remember, this is 25 times something bigger than 3. So this is like 75. So this is going to be a positive number. Don't be tempted to think 25 pi, that's actually smaller than 48. This area will be negative. It will not be negative. It is a positive value, but we just want to leave it exact. Okay, I'm going to stop here on this video, and I'm going to let you try example 5 on your own, and we will talk about it when we get together. Great job, and if you have any questions, like I said, we'll talk about it when I see you in class.